So model-driven software engineering is kind of a new concept coming down, and I did a little spin to it, calling it metrology-driven software engineering. So this is just our take on how we see model-driven software engineering coming into the metrology world. So to pull something from Mr. Fuller, right, that you're never going to change the existing reality by keeping things the same. You're going to change the existing reality by completely obsoleting the existing model. And that's kind of where we are in metrology. There's a lot of things that we do in metrology that we're doing on an old model that's antiquated, and we've got to get away from this old way of thinking. So one of the things we put together with the NCSLI 141 committee is we looked at all of these things that happen inside of the metrology world, all of the entities. And across the center here, these are the documents that we typically use in the metrology world. So you're going to grab manuals and instrument specifications, you're going to pass certificates of calibration, and you're going to use scopes of accreditation. Those are the main documents that we use. And then the entities are going to be the consumers of metrology and buyers of test equipment, and then the manufacturers, the calibration entities, and the accreditation bodies. And the NCSL 141 committee, we wanted to sit back and model a better way to do this. So instead of working with the trillions of certificates of calibration that are created every day, we started looking at the accreditation bodies, and you only have dozens of them around the world. A lot of countries have one accreditation body in the country. In the US, when we started this, we had 5 accreditation bodies. We're down to 4 accreditation bodies. So we thought this was a smaller group of people with a smaller data set, but the data set is just as complex as everything. And when you look at these arrows that sit between these entities, this is where we're exchanging these documents back and forth. And we want to digitize these documents. We want to move into the digitalization age and start moving these documents back and forth. So we started in here, but there's a lot of other organizations that are trying to bite off the big elephant with the certificates of calibration. So there's the PTBs, DCC, DOE, PSL, NPL, Fluke. A lot of people have came and started working in this certificate area. And that's where we're seeing a lot of advancements coming on, is in that certificate of calibration area. But we believe that we built a better model starting smaller data set out of the scopes of accreditation. So what the DCC and PTB are really working on is getting the calibration entity to give a digital representation back to the customer. That's the digital certificate of calibration. That's what a lot of people are talking about going on in the industry right now, is just that transaction. And me personally, I think that when we're done with all the things that we can digitalize, that getting a digital copy of your certificate of calibration, that is going to be the least valuable thing that's going to happen as we digitize metrology. So the place that CalLab Solutions started with is this concept of a DCR, so a digital calibration request. So a company wants to get something calibrated, and they want to tell their calibration provider exactly what they want calibrated on it. That becomes a digital calibration request. And we looked at that as doing that in such a way that we could get the data that a customer wants collected, send it to the calibration lab, and get that data back and automatically import it into our system. So that was our take with Metrology.net and CalLab Solutions when we started getting into the digitalization of stuff. What we see happening is we're going to come back in here and we're going to build something that's going to be a model-driven system. What we need to do, the big concept, is we need to make something that's very generic, but is still very detailed. We need to make it a simple way of communicating the message, but make it descriptive enough that we can apply it to all disciplines of metrology. And that's the hard part when you sit back and look at this, is how do you do that? So one of the places that they've used in model-driven engineering is electronics, right? So most people who work in metrology and the electrical side or been through any of the training know how to read an electrical schematic. And what happens is those symbols that they use in the electrical schematic, what happens is those guys have representation of meaning. You look at something, you know that it's a capacitor, a resistor, or an amplifier, right? So you can read the schematic and get the message as to what the schematic's doing. The model-driven engineering part comes in to when they moved it into CAD, right? And now you could use a CAD drawing to draw out your schematic. Then somebody came along and put simulators in. So when you put in the voltage at a certain point and a resistor and a capacitor, you can simulate or mathematically calculate how the software or how the electronics are going to work together. And now you can change values to make a circuit do what you want it to do without having to build the circuit. That's model-driven engineering. Then somebody came along after that, and they started putting the physical size and layout of the components, right? So once you had the physical model of it, now you could do auto generation of board layout. And that became something you could do with this. So the idea is you build this model, and then you start building things that work on top of the model, and you build more things and more things and more things. So electronics is one example. Another example is the language of math, right? We can talk mathematics and give people formulas that speak no English, and they can understand a formula as another model that you can convey information to people. Simple, transportable is what you get out of that. Universally accepted. Another one that I work with a lot is going to be databases, right? So there's a lot of tools out there where they use a thing called an object relational model. And from that object relational model, they've built tools that'll automatically go out to any language and build all your SQL script and build your tables. And you can add something to the model like first name, last name, and you might add nickname. You add nickname to the model and it automatically adds it to the database and automatically adds it to all the SQL transactions you do with that. That's all built on building this model. But the one most people understand is music. Music is another model. It's a language of talking about how music works. And what happens is the sheet music is used for any one of the instruments. So you can look at this model of how the sheet music is written, and you can translate that and play it on a piano or a guitar or a set of bagpipes, right? But all of that sheet music comes together and it becomes a way of talking music on a paper format. So now back to these different things that are going to happen around this metrology model. What we're going to be able to do as we start digitizing this is a company needs to go out and buy a piece of test equipment. Right now, you've got to go out and do a query, grab a whole bunch of manuals. An engineer opens up the manual, he reads the manual, and he figures out if the piece of equipment can do the work or not. Is it accurate enough? Is it not? Imagine having a set of your measurement requirements in a digitalized format. And now you can go query the databases, right? Just like you go look up flight information to travel somewhere and you can see all the airlines. Imagine if there was a site where you could go query your measurement requirements against all the known pieces of test equipment, and it could start selecting what pieces of test equipment can make all of your measurements, right? That's something that you can do once we get metrology in the digitalization. Once we get all of this stuff digitalized. Another one is you're You've got test equipment. You want to find a calibration lab that can do your work. Imagine taking your test requirements for your device under test and querying all the labs in your geographical area to find out who could do the work, how quick they could do the work, how accurate they were. That all could be done with the click of a button. Things that we can simplify. You're a calibration lab and you need to get, you want to add a new discipline to your scope of accreditation. Imagine being able to take the digital representation of the equipment specs, bring that over, add your cal traceability, your repeatability, and your reproducibility, and boom, you've got something you can add to your scope of accreditation. That could be simplified if we had a strong metrology model moving that stuff around. The one that we were talking about was DCR to calibration results. Imagine that you could have a data packet of all the data you want collected and being able to move that into your calibration lab and get back something calibrated exactly how you wanted it calibrated. So, and another thing that's kind of advanced, but as we get into big data, imagine that manufacturers can use the calibration, the historical calibration of the assets that are out there, and they could go back and increase their specifications or decrease their specifications, because when they did the study, when they made it, they had a wide margin because they weren't sure. But 3-5 years later, they discovered their equipment's behaving way better than they originally thought it would perform. Now they could come back in and lower their specifications or make their specifications look better with real world data to back it up. So there's a lot of things that we can do. One of the ones that I did was our software was set up to where as you run a calibration, the software can look at the scope of accreditation and never generate a measurement uncertainty that's lower than what is listed on your scope of accreditation. So that's something we see as being powerful that we can do with the model. And there's tons of other things that you could do with this. One of the ones that's, kind of crazy out there is you could take the manufacturer's specifications, right? Or you could say, hey, I want to use a military spec and I want these things calibrated, pass that down into your measurement entity, your calibration lab, and they don't have to go in and automate everything. They can come in and use that data packet and automate pieces, parts of that with no code to low code that's actually implementing that automation. These are things that are all feasible inside of this model. So another one that's really out there is going to be this 95% confidence minimal tests. So now imagine that you got this big population of data, and you as a measurer, you as a customer, you want to save money on calibration, but the calibration lab is still going to charge you because it's labor. Imagine you could look at all of your high failure data points, your medium failure data points, and low failure data points. And you could statistically pick the data points that you want to have calibrated on your devices based on how you use it and where that make model fails. And you would have the statistical data behind that you could get a 95% confident calibration with a minimum set of data points that you need to check to make that happen. These are all things you could do with getting metrology into a big data paradigm. So when we did the scopes of accreditation and we started grabbing all of this data, we discovered that there were some problems where we needed to build a model that's more than just a certificate of calibration or just a scope of accreditation. So these are things that we found on our data points when we went out and found this stuff. One of the things we found on a scope of accreditation was 30 FPM. What do you think FPM was for a unit of measure? Want to make a guess?
Frames per minute.
It's a good one. So a lot of people think feet per minute as a speed.
Yeah.
Right. We had to call them and ask them. That was flashes per minute.
Okay.
Was what was on their scope of accreditation.
Okay.
But
well,
you can see how things get messed up. You want somebody to measure feet per minute and you send it to a lab that's going to do flashes per minute, right? that unit of measure just isn't good enough. Another one is 1.2 G, and I love this. What do you think 1.2 G is?
That to me is acceleration.
Yep. Yep. And you're one of the few people who get that right. Most people think that's grams, right? And that's what you would expect most people as it comes across. The other one's a little bit easier, 10 degrees. But are we talking plane angle, or are we talking phase angle, or are we talking temperature and somebody was lazy and didn't put in the unit?
I see. I would look at that and assume that that is an angular measurement, or actually it would be a plane. It would be. I'd be looking at 10 degrees based on 360 degrees. That's
Okay.
how I would do that.
Yep. So you would look
Because,
at it as a rotational
yeah,
angle. Yep.
yeah.
So, but these are things that become a problem as you're going to move data back and forth. You can't rely on the unit of measure. And then the other thing that comes in there is to use XML, JSON, PDF. Moving right along, what we created was this idea of a metrology taxonomy. And the idea behind this is we're going to come up with all the different ways that we make measurements, but we're going to look at them as being generic, right? So how you would source current DC is just the generic definition of it. It's not any equipment specific thing. It's just like a generic interface or a generic way of describing this. And we want to get all of the measurements out there into this taxonomy database. And we're about 250 of them. And we think we've got, 5 to 10% of all the measurements that we make in the world, all the metrology things that we do. So, but what we've also found is this amount that we have that comes off the scopes of accreditation, that's the majority of measurements that we make in the industry. The idea is you come from a root, you're either a source or a measure, and then the next value here is the quantity, the thing that you're counting, quantity or aspect. And then you start getting more and more detailed. So if it's a voltage, is it an AC voltage or a DC voltage? If it's an AC voltage, is it a sine wave? Is it a square wave? Right? So you can get more and more detail in how you put these things together. And we took this idea, the reason we call it taxonomy, is we took it from the tree of life, right? And we see that pyramid as being very similar to the metrology pyramid. Is as you start looking at this stuff, and you're going to come in and you're going to take this taxon of source voltage AC sine wave. You're going to take that taxon and it's going to say you've got two things you've got to give me. You've got to give me voltage and frequency, or we can't talk about AC voltage without those two things. Then you can optionally give it, an infinite number of additional pieces of data. So you could give it the impedance, the range, and the UUT. And then what happens is you've got this procedure to calibrate a voltmeter, and it's got this definition of its calibration, which is talking that language like a sheet music. To calibrate me, you need to give me an AC sine wave of a certain voltage, a certain frequency, and you can do it with anything that can give that value out. So you could do it with a single calibrator, an AC power supply monitored by a voltmeter. You could give it to me out of any device that can do that, and I can consume that and move on. So then what happens is when we build out that data point and we're going to put that thing that's in there, that's going to be that language we pass, we can put in things like our nominal value, our upper and lower limit, what is considered a pass is within limits, a pass or equal to within limits. And we can put that taxonomy, and now we can pass that into any one of these different drivers that's able to consume that sheet music and start iterating through the processes. So now you could calibrate it on a 5720, a 5520. You could do it on a 5520 that you characterized. So that morning you took a bunch of measurements and you know how it's behaving, and you can use better than 1 year specs. You could do drift analysis. And the software that you made in your data point around this sheet music, it's already ready for new calibrator 1 and new calibrator 2. because nothing that you wrote in your definition ties you to any device that's doing that work. So, and then you look at something that's that becomes a little bit more defined in the settings. Is you're going to give it the voltage and the frequency. You're going to tell it the input impedance. You're going to tell it where it's going to connect it on the front. You're going to tell the UUT what range you want it to go to make that measurement. And you can give it, 10, 20 different things that become specific to how you do that. So now to control the unit under test, you make this simple script that I call them. And for a measurement device, you're going to write a script that says, this is how you reset the meter. This is how you set it up to take that measurement. This is how you take that measurement. If it's a sourcing device, you would do an output on or an output off inside of your script. And now you've given it the data point, you've given it the pass-fail requirements, and now you've given it a script that tells it how to communicate with the unit under test. And this is how the script would look for that. Very simple things where you're going to put the UUT range in, the UUT filter. You're going to just inject those values in the commands before you send them across the bus. And then what happens is those three things come together with your standardized metrology process that you've created. They come together inside of this blue code. And instead of making flexible drivers, we've made flexible units under test. So now your unit under test just plugs into your metrology process. And you can go from a single calibrator to a calibrator that's verified with a multimeter, and you could monitor it while you're doing it, chart it, drift it. But this unit under test just becomes a plug-in, and it just all comes together and works. So that's the idea behind it. And when I did this presentation, I did this before the 5560 was ever added to the market, and I did it before the 9010 was ever added to the market. So now that those calibrators are available, all you have to do is write your process for new calibrator 1 and new calibrator 2, and all of a sudden, all your devices that you've written software for now run with the new calibrator that you bought that came into your lab. The day it hits your lab, you've got thousands of procedures that are ready to run with zero code changes. And that's the power of the model-driven software engineering from my perspective. So, questions?
Technically, my brain wants to relate it to Metrack.
Yep, when you're saying Metrack, I'm going to assume you're thinking Mudcats.
Yes.
You'd have your data sheet, and then you could go find the standard that can do the work. Yeah,
it's called SpecTrack. Sorry,
SpecTrack. Yeah.
Sorry, it's been a long time since I thought about that.
Yep.
So SpecTrack. So I'm relating it to that.
Yep.
Because that concept was pretty cool back in the day when we were, plugging in data sheets, and so we had to, anyway. So that's kind of what I'm relating it to. Although it's updated, but the concept is the same.
Yeah. Yep. When I started playing with SpecTrack, in the back of my mind, I had that same thing. You had an input or an output, and then you had these functions behind the output, or the input and the output. So you guys organized that exactly how I saw it in the back of my head. The only difference that I brought to it is this idea of a taxonomy being a more detailed way of looking at how to find that information. But yeah, the SpecTrack was definitely revolutionary, and you guys had coded it. Why, it was just an idea in my head.